just x. In explanation, I used x0, x1, x2, x3, and so on, right? But in actual program, I use x, 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 x. So computer just to reset the value each time, right? It was x0, but now next time, even though we use just 1x, it resets the value to x1, right? Resets value to x2 and so on. So we have these things, and roughly we did these things to find the solution to this problem. And the key part is this formula called Newton's iteration formula. So deriving this is the paperwork. In other words, researchers should develop these kind of things. Of course, if someone already did it, then you cannot publish the paper. But if yours is new, then you may be able to publish it. Any questions? Then what else did people develop? There are about total 7 methods that I want to cover, and a few technical definitions will also be covered. For instance, x equals, I want to solve this kind of thing. I want to solve this kind of equation. X equals cosine x. So one idea was Newton's method, right? One idea was Newton's method. So this can be done. Oh, I can define f of x, and f of x equals x minus cosine x, right? Then this should be 0, right? This should be 0. Then f prime can be found. F prime of x can be found, and it is 1 minus cosine x derivative, right? And it is 1 plus sine x. Then we can use Newton's method. So we can determine x out by x in minus f of x over f prime of x. So it's one idea of solving the equation, right? This is Newton's method. But there is a different method, or possibility of a different method. So I will show you the idea. So this is Newton, but the next method is different than this one. What is it? X out becomes cosine x in. Why? Because we had this equation, x equals cosine x. So I change the role. This works as in row, right? Input row. This works as output row, right? So I change the role of x. The right hand side x works as the input. The left side works as output. Do you follow me? Then this becomes perfectly working example. So let's run it. Once you complete, then I will run. Once you write down these things, I will run this.
So are these notes going to be online?
Yes, already online. I mean, this exact note, right? Yeah, it will be online. And what I meant was the summary note of this is online. So I will show you the summary note. As you can see, it's perfectly summarized here, and it's perfectly summarized here. So let's run it. After minor modification, f is here. df we won't use. How can you comment this out? Percent? This comment out. And the next one is okay. And then instead of this, I can just replace this by cosine x, right? This is it. And then I can save this as, I save as program 2. So I essentially did it, and I will run it for 3 different values, right? 3 different values. Do you follow me? So I'm running this thing. The only change that was made is this one, right? Right? This is the change. Then let's do it. save, and then now let's run. And instead of running blindly, I will just set the breakpoint here and then run. So let's run. So you can focus on x and I. I you don't even have to worry about. I is artificial. So you focus on x. X becomes what? 0.54, right? And then 0.85. And so, right? So we got this kind of result. Oh, I should. So do you completely follow me? We are solving this equation, and then I ran it, and I will run one more time. Look at the change of x. X is 1 initially, and then because of this line, x will change to 0.54, and then x will change to 0.85, and it will end, right? And then it will print out this one, right? And now I will increase this number. I will increase the number to 10, right? Then without any breakpoint, let's run. Then it calculates the result, right? It calculates the result. Then let's really solve this thing. Solve x minus cosine x. What should I do? Equals 0? Do you know, have you ever used solve command?
You have to
Find? Oh, then let's not go into that kind of it. We don't want to go in that. In any case, we ran this thing to find the solution, right? We ran this thing to find the solution. And let's see the change of x step by step one more time, and then go to the next idea. So 1, 0.54, 0.85, 0.6, 7, 7.2, 7.5, 7.3, 7.4, 4.2, and so, right? So it might be stabilized or not. So let's verify this thing with the different method. So I will include Newton's method here to check the result. So Newton's method, Newton's method. Function should change. Function is what? X minus cosine x. And derivative is 1 plus sine x. And this should change. It is x minus f of x over df of x, right? And then let's run. So you remember this value, 0.7442. With Newton's value, we get different result, right? So this means we need to run these things for bigger values to settle the matter, right? So let's run this for bigger value. With Newton's method, it is already stabilized, right? Then iteration method might have some flaw or require more iteration, right? So let's change this to iteration and then run for 20. With 20 has a better value, but still the last digit change I observed, right? So let's increase the number of times, then it is stabilized. So as you can see, depending on method, the convergence rate might be different. Any questions? So I covered the iteration method. So iteration method essentially iterates, right? So the left-hand side should be x, and the right-hand side could be any function. So take a look. Iteration method and Newton's method has different setting. Newton's method, you must write the equation this way. iteration method, you should write the equation this way. Right? And if you want to use Newton's method, you should move this to the left-hand side and derive f. If you want to use iteration method, you should somehow extract x on the left side and create the g. So you should see the similarity and the difference. Newton's method uses f. Iteration method doesn't use f. It uses g. So as you can see in the program, I didn't use f here, right? Did I use f in the iteration? No, right? I just used g, not f. I will save this thing. But before saving it, I will erase this unnecessary part, right? So you can easily look at the program. Generally, it's possible to write g function upstairs. G function is equal to cosine x. Then you can call g function. Do you follow me? Then the only line that you need to change is this line when problem changes. Then the next method is my favorite method. It's this method. Bisection method. It's like this. Assume that we have a solution, then it means it hits the horizontal line, right? Solution usually, when you graph it, it hits the horizontal line, right? So this is the solution, right? Then bisection method depends on this idea. Theoretically, it depends on intermediate value theorem, but practically this is the idea. Assume that this is the water surface. One is inside the water, the other is outside the water, right? One is inside the water, the other is outside the water. Then, if the line is continuous, if this line is continuous, it should hit the surface, right? No matter what. No matter how it is bent, it should hit the surface, right? Right? No matter how it is bent, it should hit the surface. Do you follow me? Right? One is inside, one is outside. Then to track down the hitting point, we bisect the domain or interval. So for instance, at one point it's underwater, on the other point it is over the water, right? So under, over the water, right? Then it eventually hits this point. Then how can you track down? We have this point, right? This interval is bisected, right? We have this interval, and then check whether at this half point it has 0 or over or under. So only check we do is whether it is the solution itself or over or under. If it is the solution itself, then we can stop because we have found the solution. But if we are not that lucky, then it may be over or under. Assume that it is over in this, so I will give you actual problem so that you can really follow. So assume that we have underwater, over water problem, and then we bisect Wow, I'm sorry for this, because it is a little bit bad to determine. Assume that you have this thing, then we bisect, right? At the bisection point, assume that it's not the solution. It's not the solution yet. Then we only check whether at this point is above the water or under, right? Under the water. So that's the one we want to check. So if it's above, then we can shrink the focus interval. Initially we focused on this interval, right? We focused on this interval. And now, after bisecting it, we don't even have to worry about this portion. Why? Because over case, right? So we focus on under case. And then after this, we bisect the interval, right? We bisect the interval. And then we check whether it is over or under. If these are over, then we don't have to worry about this part. Only opposite signs are worried. Then afterwards we bisect our interested interval. Then should we look at under or under over? We should see under over. In other words, each time we bisect and then shrink the possible area of search. In other words, we exclude this kind of unnecessary part, and then we focus and focus. So this is the bisection method. And there is an advantage and disadvantage. Disadvantage is the speed, because it bisects the interval each time. Assume that we have a big interval, then we should bisect many times. So it may be slow. But the advantage is it guarantees the solution. Guarantees the solution to any accuracy level, It always tracks down the solution inside the given interval. So there is a huge advantage. And even the speed is not bad. Why? Assume that you have found that at one point the function is under, at the other point the function is over. Assume that one point is in Chicago, the other point is in Illinois. Chicago, in San Francisco. So one point is in Chicago and one point is in San Francisco. Like about 1,000 miles, right? Then how many times should we shrink? One shrink gives us 500 miles, 250, and so on. So after maybe a few steps, less than 100 steps, right? It may shrink enough. Right? So dissection method isn't that slow, but people regard this the slowest method, right? In any case, this is it. So if you have a question, ask me. If you don't, then I will continue and cover the next case. If you want me to program this thing, then I will show you how to program, but it's not that difficult. Do you want to meet the program, or you can do it? Oh, excuse me?
Program. Please show us please.
So let's design it first. So I will call this underwater, right? So underwater, and then I will call this overwater, right? Overwater. So UW represent underwater, or it's not a good choice, but yeah, because it is too fixed. And then I will call this middle point, right? Middle point. So we have already three cases, right? We have three cases. Then what I will do is this one. We use f of underwater case should be always less than f of overwater case should be. So this is our assumption, right? Under this assumption I will program, but if you want to make it different, then that's okay too. In other words, always opposite side is okay. One thing could be up, the other thing could be down, right? Yes?
What about some kind of curve that...
It doesn't matter. I will show you. It doesn't matter. So take a look. right? At point to over water, right?
Right.
And then underwater, right? And then you can bisect it. Then this is over water, right? Then we ignore this part, right? We ignore this part. And now this becomes over water. And then we pick the middle point. And then we bisect this thing and check. And then this is disregarded.
What if you had bisected, or what if you bisected it in the part that's been under?
And if, for instance, if you bisect and it's under,
Well, no, but like in the first case, like you had the 2 points,
Uh-huh.
and you went to the middle. It was clear that it was over, but it had been under.
then you exclude the other side. In other words,
Okay. Oh, okay.
Yeah.
All right, I got you.
so if this happens, and then bisect, and then these are underwater, then we pick. So you either pick this or that.
Okay.
So we're only looking for a solution, not the only solution, or
Just one solution, not all solution. Good point. Later I will mention about all solution consideration, but right now, one solution. In other words, we dumped this solution, we are even not including these things in consideration. Good observation. But we are focusing on one solution. So this is the situation now. Middle point is the average of over water point and underwater point, right? Average of these two. Then, if f of m is 0, then stop, right? Print and stop, right? Print m and stop. Print m value and stop. Why? This m value is the solution because f of m is 0. This is our goal, right? This is our goal. If m is 0, then you can print m and stop because m is the solution. But usually we are not this lucky. So we should say whether fm is over water, right? If fm is over water, then this is the thing you need to do. It's not actual program, it's pseudocode, and later I will write a program. Then over water value becomes m. Another m is assigned to new over value because over water is has two positions already. You don't need two positions, just one position is enough. We just maintain one underwater, one over water, right? But already one initial position was over water, but you have a second over water position. You don't need second over water position, right? So we dump one unnecessary over water position. Then one over, one under. Always we keep one over and under. This is it. Do you follow me? Or if it's not, in other words, it's less than 0 then. If this happens, then we stop. If this happens, over water is m. If this doesn't happen, that means it's underwater. Underwater is m. And then end, right? So we essentially relocate underwater or over position depending on middle point height, right? If middle point is over water, then we dump unnecessary over water. If it's underwater, we dump unnecessary underwater. So this is what we do. And then we iterate these things. So let's really program, unless you have a question. So, what do we need? We essentially need the function. We essentially need the function f, right? So I'm browsing my design and then check what we need. We need underwater point, overwater point, and middle point, and then F. That's it, right? Over order, under order, and F. And then M is determined by the average. So let's do it. F is any function, for instance, x minus cosine x, right? So we are solving x minus cosine x equals 0. Assume that we are solving x minus cosine x equals 0. Then we start off with over water equals something. But we don't know what is over water and what is under water, so I will suppress this thing and then just run this thing to store F and then calculate F of over water. Is it really over water? So I calculate F of OW, right? Is it over water or under water? And answer indicates F of OW is what? Over, so it's okay. Now I will pick underwater, so let's pick any value. W underwater is like 0, and then let's check whether it will work. And then I will calculate F of underwater. Is it underwater? Take a look. Right? F of underwater. So I pick 2 points. One is over water, and the other is underwater. Then we are ready. We are ready. Middle point is average of the two. So I will show you the progress. I'm doing this part. I'm doing this part, right? The next line I will do is this part, and the next line I will do is this part. So I will follow these things. So the next line is this. If f of a middle point is 0, do we need then here or not? Then
Not usually. Only use whatever follows that.
print m, right? Print m. Else if all connected, f of m is over water. Did I use over water? It doesn't matter, but I want to check. If f of m is over water, then over water is m. Do you follow me or not? I will suppress the output. I will suppress the output. And else. Then underwater is m. And the end this if. So I finished programming these things, and if you have a question, ask me. If you don't, then I will run. So please browse these things and ask questions. So we have overwater point, underwater point, right? And middle point is nothing but the average of the two. Now, checking the middle point, and then assign new overwater point, right? New overwater, new underwater point, depending on the position. So if you don't mind, I will begin to run. If you have hanging difficulties or questions, ask me. Then let's run. After breaking here, let's run.
You're not showing anything. Everything's suppressed.
Right. I'm not showing anything. Is that a problem?
Well, I don't think print is a valid
Oh, then what is?
Just and.
Ex-
It would just be type of
Oh, I see. I see. Thank you. Because I happen to use other language. I initially used Mathematica, and initially when I came here I used Maple, and recently I converted to MATLAB because department decided to buy MATLAB. So let's run it. What is the problem? Line 5, columns 13. 2 equals? Phew. So let's run. So you should look at 2 things. Over water, underwater, right? You should look at 2 things. So take a look. Over water is 1, right? Underwater is 0. And then middle is now created, 0.5. And then check. And it is not a solution. We are not lucky enough. And then if it's greater, it's not greater. Why? As you can see, f of m is not. So to check this value, let's type one more time. F of m is what? F of m is negative, right? Underwater, right? So it couldn't go into. Now it should go into this part, right? Right? Now take a look at overwater, underwater position. Initially it was 1, 0, but now it is underwater position has been updated, right? Better position. We don't need overloaded underwater position. Just one underwater position is enough. So one is underwater, one is over, always. Now we return back and then go middle point. Now new middle point, right? And then we better check. We are not lucky enough, right? And then check. Oh, why? Let's check f of m. Because f of m is what? Over water or underwater? Over, right? So, over water, there is already initial over water, but now middle point is also over water. So we change it. So now take a look. Over water is this, underwater is this. So now the focus area interval is between 0.5 and 0.75. Now we go to the next case, but unfortunately I didn't run it enough time. Oh, it's enough time? So let's check it. So it passes. That means it is underwater, right? F of m now is underwater, as you can see. Underwater. Minus value. So there are 2 underwater values, 1 overwater. There are 3 values always, right? 1 underwater, 1 is overwater, and then middle value. My middle value is also underwater. So we don't need 2 underwater values. So we update the underwater value. So we should update the underwater value at this position. Now it is updated. Because I ran only 3 times, it stops. I ran on 3 times, it stops. This is it. Any questions?
Does it display negative signs?
What do you mean by negative? This one, you mean this one?
The water right now is negative 1.8. That's f of m.
F of m each time. I want to check whether middle point is over water or underwater. So I want to check whether so to help you, at each time I will add this name. F val will be written. F val is nothing but for the debugging purpose I'm adding. It's not necessary, but for the debugging purpose I will add. Then you can focus on F value instead of writing, looking at this thing. Then it will be very clear. So let's look at it and then save it and then rerun it with bigger value. I run it for 7. So let's do it. So take a look. Now f val is here. F val is under, right? And then go ahead. Under will change, right? Under changes. Now f val is what? Over. Then over will change, right? This will change. So take a look. overchanged, right? And then FL is under, right? Then it changes. Under will change, right? This under will change. So we continue these things, then automatically computer calculates whether it's over or under, and then determine these things. So once you set up this correctly, then you did continue and continue, and then determine the value. So what happened? Did I run 7 times? Oh, already 7 times. I hit this. 7 times are not enough. Then I will increase this value by how many do you want? 20, right? 20 is enough. Then instead of breaking this thing, let's not break at all. Let's run it. Then the over water value is this one. Under water value is this one. Middle point. Or take a look. All these are the same, right? All these are the same. Essentially, 0.7391 is the solution. You may remember this number. I used Newton's method and iteration method to solve the problem, and I got these numbers. Do you remember these numbers? Yeah. So bisection means over and under, and then we shrink the interval to track down the solution. And it's exponential speed. Why? As I mentioned, one in Chicago, one in San Francisco, now about Denver, and then Utah, and then Illinois, and so on. And then it goes on and on and on. Very close, very fast.
So exponential.
Right, exponential. Right. So I will save it and go to the next. So this might be the last one I show you the implementation. From this point on, you should implement your own. So I will save it and go to the next page. So bisection is covered. Then what else people developed? Because they already occupied nice, Newton occupied nice thing, iteration is occupied, and bisection is occupied, then twist of these things might be necessary. So I will let you know what things are covered. So let's go to the summary. The next thing is this method called regular force method. And I heard this Italian name or something, force position. So regular force means force position. And the meaning is artificial ruler. And it's almost identical to bisection method, but there is one twist. So let's do it. Take a look. In bisection method, assume that this is underwater and this is over water. And if it looks like this, then we bisect and bisect and bisect, and the speed is slower. As you can see, we bisect and bisect and bisect, and then at least 1, 2, 3 times bisection leads us to the point close to the solution. So people consider this kind of idea. What about instead of bisecting, somehow dividing the interval using some kind of proportional change? In other words, I can connect these 2 lines. I can connect these 2 points, and then I can divide the interval not by bisecting, but by just cutting the point like that point. Do you understand what I mean? Instead of just middle point. So the idea is this. Idea is instead of middle point, instead of the middle point, So instead of middle point, we use proportion between the heights. And then we divide the interval unevenly, right? Unevenly. Then we may speed up the result, right? That's the goal. So idea-wise is bisection. Idea-wise is bisection, but it's not the middle point bisection. We go close to the proportion, right? If it is deeper, then we go closer to the narrow, if the distance in one side is bigger, then we go to the other side, right? In other words, closer side we choose. So as you can see, this distance is bigger than this distance, right? Then because of this proportional difference, we chose like 1/3 point instead of 1/2 point, right? 1/4 point instead of 1/2 point. It doesn't look even 1/4, so 1/5 point instead of 1. So depending on the proportion, we choose point differently. So completely bisection method, only difference is the decision of determining the middle point. It is not middle point. So in actual program, everything should be the same, except the determination of middle, right? We used to really choose middle point. But it should not be middle point. It should be chosen by proportion, right? So middle proportion point should be chosen. This is the difference. All others are essentially the same. Do you follow me?
So the program for this and the last one is the same, except how
Right, how we determine middle point. In the previous program, we just do the average of the 2 points. But now, we do technical calculation to determine the middle P point or MP point. So only difference is between M and MP. This is the regular force. So only change is middle should be replaced by middle proportional point, right? Not just middle proportional point. In program, you can use letter M, because M doesn't mean anything, right? In program. But determination of M varies. That's the only difference. So let's find it. It requires like maybe middle school algebra. So you should do the proportional calculation. So assume that this height is f of underwater, right? Height should be f of underwater, absolute value of, right? This height is f of over water. Do you follow me? The height is f of over water, f of underwater. Then, can you find the proportional point? Is it too difficult? Then you break this and then copy this here, right? So you copy this and then f underwater, right? Then you can use the proportion. What is the proportion? This over this one, right? This over this one is the same as this over this one. Do you follow me? When did you learn these things? Middle school? This over this is this over. So this thing is required. So let's do it. So I will call this size, I will call this length. So it's only decision time. So you can call these things by using any letter. So let's call this length A, right? And let's call this length B. Of course, this length is the copy of this length, right? This B length is the same as this. So length B. Then length B over length A equals, right? Length B over length A equals length F underwater, absolute value, right? Over F over water, absolute value. Do you follow me? It's algebra stuff, right? Geometry stuff. So ratio B over A is the same as ratio this. then you can multiply let me briefly check what is necessary afterwards. The whole interval has this is underwater point, this is over water point. So the whole interval a plus b is over water minus underwater absolute value, right? So we have two unknowns a and b, right? We have two unknowns a and b, and we have two equations. So we have two unknowns, two equations, meaning we can solve the equation for a and b, right? We can solve the equation for a and b, and we can eventually determine the position, right? We can determine the position how? Underwater times middle point a equals underwater time plus b, right? Underwater position, and then we add b, then it's the position. So by doing this calculation, we can derive the formula. But it's not, our course is not elementary. MP, right? MP means M, because we don't have any more M. MP and M are the same. Good. So we determine the MP position by adding B to M, the underwater. So this is all you need to do. And I did this calculation and derived this. So look at the formula. It looks like this. So I used, instead of underwater, over water, I used B and A, right? I used B and A. I used B and A, and then determined the MP point, right? So B and A are underwater overall points. So any questions?
So the midpoint is B minus F of B times
That's times.
quantity?
Right, that quantity. So I will reprogram our things because only one line change should be made, right? Only one line change, right? This line is not middle anymore. It's any point in between, right? Any point in between, especially proportional point in between. So it should be B minus this thing. I forgot what was written. B minus, so B is over water, right? Over water minus F of, I have notes, so I will see the note instead of. So if you already printed out the note, then you can just look at your notes. F of, so A is underwater, B is over water, so over water multiplied by F of over water minus F of underwater over, this is not over. So this is it. So this is the formula that you can derive from middle school geometry. Do you follow me? Yes?
Can you introduce the brackets because it would have multiplied F over water times
So you have matching stances, right? So any questions? The only difference between the previous problem and this problem is the middle point decision, right? Instead of using M, we use MP, but in program we still use M. Then let's run it. So instead of 20 times running, I will use 3 times running and follow it. So let's do it. File save as. Did I save it? I deleted 3, but you can easily recover 3 from 4, right? Because the only thing that requires is the M decision, right? M should be just average. So let's run it. After breaking it, let's run. And then step by step we follow. So now the middle point decision, overwater position is 1, underwater position is 0. Now the middle position should be between 0 and 1. In the past we had 0.5. Middle point is 0.5, but now look at what happens. The proportional position should be what? This one. Instead of 0.5, it is closer to the overwater position. And then, now, everything is the same, right? Everything is the same. And then return back, and then now, middle point should be determined, right? Then, it is 0.7, right? So as you can see, it is way faster than general bisection. So essentially bisection with twist, right? With this twist to speed up. Done, right? We are done. Any questions? So regular 4C method means we use the biased middle point instead of middle point. So I will recover the bisection method from this thing by just saving this as, and now no harm done. Any questions? The next method. The next method is similar to Newton's method. The difference is this. In Newton's method, we had this situation. X out equals x in minus f of x in over f prime of x in. This was the Newton's method, right? And now the problem is this. Assume that we do not have derivative. We do not have derivative. Then how can you replace the derivative? How can you replace the derivative? So this is the idea. Right, that's it. That's it. So that's the key idea. So we now replace everything by the approximation. So suddenly instead of x in, we now have x in sub 1 minus x in sub 2, right? X in sub 2 over x in sub 1 minus x in sub 2, right? And then here, x in minus f x in, right? So suddenly we need this approximation approximating x in derivative because we don't have x in derivative. Do you understand the idea? Do you understand the idea or not? We suddenly need something replacing f prime of x in. So f prime of x in is replaced by x in sub minus this. This is similar to the derivative, right?
Did you really mean x out on the left side of it?
Oh, sorry. I mean, I was confused between the formula and this one, so I should retract myself. I'm confused between the formula and this one. So what I meant is just f prime. Yeah. I wrote down the formula itself directly. So we should replace x in prime by this thing. If you don't understand, ask me. Then take a look. I now replace this by x in sub 1 and x in sub 2. Difference, right? Then what about about these things? What about these things? What should we do? You can do any way you want, but use 1. In other words, if you choose x in 1, then use x in 1. If you want to use x in 2, then use x in 2. Do you know what I mean? So either use x in 1 or x in 2 consistently. Because we are replacing x in by x in 1 and x in 2 difference, those x in should change too. Because we don't have x in anymore. We now have x in 1, x in 2. So we should replace x in there by either sub 1 or sub 2. You may pick anything and use the chosen one consistently. In other words, you don't use x1 in here, and then you don't use x in sub 1 here, and you don't use x in 2 here. No. So either use x to x2 or x in 1, 1. Right? So choose 1 and use. So what do you want to use? 1. Then I will rewrite the formula. X out becomes x in, did you say 1 or 2? I forgot. 1 minus f x in 1 over f x in 1 minus f x in 2 over goes up, and then x in 1 minus x in 2. So this is the secant method. So Newton's method and secant method have the same origin, even though formula look very different. Yes?
In your notes it's x1 minus fx1 times the quantity, and on the board you've got x in 1 minus. I guess in the notes the first f of x in 1 isn't over quantity f of x in 1 minus f of x in 2.
You can write it, you can separate and write it. Either you move up or you can use it in front.
Okay.
Yeah. So if you have a question, ask me. If you don't, then I will continue and explain that. So very strange thing is this. Formula-wise, bisection, regular 4C and secant method look exactly the same, formula-wise. Why? Because we are doing proportional calculation, and I will show you the formulas, and you can tell me the difference. Formula-wise, this is the regular 4C, this is the regular 4C, and this is the secant. Can you distinguish one from the other or not? Take a look. Can you distinguish one from the other? Assume that M is x2, B is x1, A is x0. Can you distinguish one from the other? So formula-wise, regular 4C and secant look the same, but idea-wise completely different. Why? Regular 4C is bisection disguised, right? Bisection disguised. Secant, Newton disguised, right? So they are completely different, but because we are handling the same problem, formula level, they look the same.
Would the answer much pronounced the same way too then?
Oh, I will show you that. It's essentially the same program, but program should be different too. So should I change the bisection method program, or should I change the Newton's method program? Newton's method program should change, not the bisection method program. Even though formula-wise, they look similar. Why? Regular 4C is bisection essentially. Only decision making of determining M changes, right? But the regular secant method is essentially Newton's method. So formula exactly. If I use the same letters, then you may not even see the difference. I may even copy and paste, right? Copy and paste. So I will show you. So I will save this thing and then I will call, I guess, first method first. So take a look. What is the function we want to handle? Let's handle the same problem. F of x minus cosine x is the one we want to solve, right? And the derivative is 1 plus sine x, right? And I want to run this thing to see the solution. So this is the solution we obtained, right? So please check Newton's method itself, right? This is the Newton's method. But now, we need, as you can see here, we need just x in to determine x out. But now we need x in 1 and x in 0 to determine x in x out, right? So this is x out, this is x in 1, x in 2, right? X in 1, x in 2 are necessary to determine x out. So we need two different points. So I will write x in 1 equals 0, x in 2 equals, 1 equals 1, right? Yeah. I used in the note 1 and 2, but in the formula I used 1 and 2, 1 and 0. So I will use 1 and 0 because I used it in the formula, but doesn't matter. You can use any subscript you want. So instead of just 1, x equal to something, I use 2d, right? And then I use the same formula, but x out is now x in, what did I use here? X 1, right? Consistently use 1, right? Any questions up to this point?
It wouldn't matter which order you put those in.
Doesn't matter. So that's the reason I said you can choose 1 or 2 either way, but you should be consistent, right? If you choose to use 1, then you choose 1. If you choose to use 2, then use, in this case, 0 and 1, right? In any case, this is it. Essentially, no big change. But programming-wise, one more change is required. Programming-wise, one more change is required. Do you see the requirement here? In the next step, in the previous case, automatically x in became, x out became x in, right? X out became x in, but now we have two different values. So there is a twist in the programming. Theory-wise, everything looks similar, right? But suddenly in the programming side, we have twist. So in this case, we should determine what should be x, right? So after this step, you can call new x in, excuse me?
X in 1 equals x.
Right, something like that. But I will, if you don't make this carefully, then you fill the variable with the same value, so you should think this in order. So what should be filled first? First of all, x 0 should be replaced by x in 1. Do you follow me? And then x in 1 should be replaced by x. If you reverse the order, what happens? If you reverse the order, x replaces x1, that x1 is also replacing x0. Do you know what I mean? You should be very careful in this order determination. When you program, if you are not careful, then you see the malfunction, because these go into the denominator, and denominator becomes 0. because you somehow populate these things in wrong order. So when you run, you should be very careful. Essentially, this is a twist you should handle. Then let's run the system.
You change on line 4, you change x in 1 to x in 0.
Right.
0. So we got it backwards up at the top. So if you just make x in 1 equals 0, if you make that x in 0 equals 0. It makes the next one x in 0 equals 1, make that x is 1.
So you should, it means,
So if we make that equal 1,
and then?
and make the next one equal 0, then it should work.
Thank you. Something is wrong. What do you think is wrong? I'll check it.
Yeah, what does NaN mean? Is that like,
I think that's divided by 0.
is that about okay.
It might be too close, right? It might be too close. So it might be too close.
We got really close to 0.
In any case, secant method doesn't have any guarantee of convergence. So you use this thing on your own, right? Because it has the risk of getting this kind of bad situation. Because they are very close to solution, almost a zero. Zero denominator is the possibility. So it has defects already, as you saw. We didn't do things very wrong, but it gave us some bad results. In any case, I showed you 4 different methods. So take a look. Let's briefly summarize what we have covered. We covered Newton's method. We covered iteration, bisection, regular for C, and secant. And the next thing is a little bit tougher. So instead of covering it, I will briefly mention about the idea part, and next time I will finish this chapter, but the next thing is this one. Up to this point, what we used is one-dimensional linear function, line, right? What we used are lines, right? We used lines to determine the point cutting the horizontal line. We have horizontal line, and this horizontal line was cut by a line. But what if we use different curve instead of line to cut the line? In other words, someone considered different idea, and instead of cutting this with a line, with a parabola, we can cut. With a parabola, we can cut the line. And this idea led us to Miller's method. So instead of using first order function, or a first order function is a line. He used second order function, quadratic equation, quadratic functions to cut the line, horizontal line, and find the intersecting point. Then what is the similarity and the difference? Idea part is very similar. So this is the situation. So I will explain the idea. We initially pick 3 points, x0, x1, and x2. Approximately these 3 are solutions. These 3 points are solutions, roughly our guess solutions. Then we can find the second order equation or quadratic function passing through these 3 points. Right? And then we can follow these things, and then this becomes a parabola and it cuts some point, right? So from x0, x1, x2 we can get x3, because an equation passing through the 3 points generally is a quadratic function, right? Second order function. So we have 3 points, then we have a quadratic function cutting this thing, and then we find this point, x3. And then, next step, we use x1, x3 to determine the next point, right? x4, right? So we have x1, x2. If it is 0, we are lucky, but usually we are not this lucky, right? We are not this lucky. If x3 gives us 0 value, then we have found a solution. But we are not this lucky. Usually it has this kind of position. Then using these 3 heights, we can determine the parabola passing through these points, and then we can cut the line. Then we can find x4. Then we're using this x2, x3, x4, we can find the next cutting point x5, right? By similar steps. Do you follow me? So this is the idea Milner developed, and unexpected byproduct happened. With this one, complex solutions can be found. Why? We solve a quadratic equation. When you solve a quadratic equation, sometimes quadratic equation gives us complex solutions, right? So the byproduct of this method is the handling of complex roots. If you don't understand, you can ask me. If you understand, then it's great. Do you follow me or not? With lines, it's impossible to detect any complex solutions. But with quadratic equations, as I showed you, we can find complex solutions. So Miller's method is used to determine complex solutions too. So roughly these things will be covered next time, and I will be here. You can come and ask questions for about 6 more minutes.